Okay, hello again. Then we'll continue. And the first presentation after the break is from Clément DEXTREIT about distributed e-drive control. And as I heard, one presentation of those four is not existent, so maybe have some more time for questions. So my heart was a little bit bleeding to interrupt you when asking questions. So we're a little bit more relaxed in the schedule until lunch break. Then I'd like to hand over to you, and we're looking forward to your presentation.
Thank you very much. So the second presentation from Changan this morning. I'm working on control strategy. So in this presentation, I will discuss e-drive control, distributed e-drive control. So I will introduce succinctly the background on advanced EV powertrain at Changan. Then I will move to the distributed e-drive system development within our company. We will see the legacy software architecture in terms of electrical architecture on the initial DEDS, which is distributed e-drive system implementation. We will move to the proposed software architecture that we push forward at CA UK for the DEDS electrical architecture on software also. And we will conclude on talk about further work. So, background. Etienne already presented the company, so I won't go through that again. In November 24, the technical roadmap was outlined in the press for the company. So it was announced that Changan will work on innovative new energy vehicle platform, internal development of advanced electric unit, EDU, and integrated control for powertrain and chassis development. In the UK, we are currently leading the inverter control software method through Etienne and Etienne's team, and actively participating in the software development of the new EDU platform. The brand motto was defined as ultra agile, ultra intelligent, ultra safe. So they want to do everything. That's nice. And from that, we're going to talk about distributed e-drive system. To fulfill our mission for enhanced agility and safety, we are developing distributed e-drive system. So basically, instead of having an electric machine through a differential, on the same axle now we will have two e-machines which are not connected to each other. Each e-machine can provide torque to the wheel individually. And we've got two topology that we will push forward. One with quad motor, so one DEDS on the front, one DEDS on the rear, and a tri-motor configuration with the rear axle still being distributed e-drive. On the front axle will be a single machine through differential. So we are not the first on the market with this type of technology. We consider different strategy for control, taking advantage of the distributed e-drive system. So we consider traction control, stability control, pull drift compensation, which is currently done by Ford using the power steering and by Mercedes using the brake system. We can consider tongue turn, which is a big thing in terms of marketable feature. If control, we can wind up the motor against the suspension when in park and just try to control the level of the car. So on a camber road, we can have the car spin straight and get into the car. Motion sickness and ride quality control can be controlled by adjusting the pitch and also eventually the roll. So for this presentation, we're going to focus on few aspects of this control strategy. So stability and wheel speed control. So we want to enhance the agility in cornering on all type of terrain. We want to affect the straight line stability using pull drift compensation. So if there is a change of camber, we can keep the car on a straight line. If you got lateral wind also, provided the driver doesn't interact with the steering wheel. We can try to keep the car on a straight line. We can enhance the launch by control acceleration and also work on the wheel slip or wheel lock control. So from this high-level view, when we dive into the type of feature, so we got the feature we need for the powertrain, then we need to develop function to support this feature. When we look at pull drift compensation on agile cornering, we think about left-right torque ratio. And when we look at control acceleration and also agile cornering, we think about front-rear torque ratio. So we will have control strategy to provide us a target ratio for front-right torque distribution on front-rear. And we will provide from that individual wheel torque request on each of the wheel on the four corners of the vehicle. For wheel speed control, it's a bit more dynamic. We are considering using for each motor on each wheel a lash crossing function, a wheel slip control embedded within the inverter, torque intervention, anti-jerk. We also need to develop some observer to support this function. So we need to have a wheel slip calculation, vehicle ground speed estimation. When you got the four wheel spinning, you still need to try to estimate your vehicle speed. Vehicle state estimation, understeer, oversteer, road mu estimation, mass on road slope estimation. Okay. Let's go back on Changan legacy software architecture and the initial DDS implementation. We are a brand coming from conventional vehicle. So at the time, we were really EMS-centric. So you got all of the ECU of the car that kind of communicated through the EMS. So we've got accelerator pedal input directly hardwired to the EMS, the ESP, power steering, body control module, all inputting into the EMS. EMS closely communicating with the transmission to provide drive torque, longitudinal torque. We moved later to HEV, PHEV, and for this, because we add a source of energy, which is the battery on the e-machine, we created a new controller in the middle. Now the EMS is a bit more of a slave of the VCU or PDCU. We are now doing the vehicle supervisory controller in this central unit. Moving to EV, we still kept the same type of implementation for cross-platform compatibility, but now we don't have any transmission or EMS. Yeah? So it's kind of simplified, but we still have the VCU at the heart of the torque management. Yeah. Okay. So what are the drawbacks of this type of architecture? I would say latency. In terms of communication, usually the torque path, we send message, even if you got FD-CAN, we usually send message every 10 milliseconds from the different controller, brake, power steering, body control module, BMS, to the VCU. And we don't really use maybe our controller in a clever way. We use the BSW basic software on one core, on the application software on different core. So it means that when we get the signal, it has to go through one run of clock through the BSW, 10 milliseconds. We go into the SW, which takes 10 milliseconds. We go back out 10 milliseconds and back out on the CAN, 10 milliseconds. Then we go onto the different actuator, EMS, TCU, PEU, optional PEU for for E4-wheel drive, and the feedback from this with the actual torque derived by each actuator, for example, will come back at 10 milliseconds, and we'll have to go through this loop of BSW, SW. So the latency from requesting a torque to getting the feedback of what this torque does is around 80 milliseconds or over. Yeah. When we look at the DDS, we obviously at HQ, they just kept this implementation and they kept this high latency inside the control strategy. So they're starting to update the torque path to provide individual wheel torque out of the VCU. And also they took over some of the wheel slip control, and then they will send that from the VCU to the inverters. A more comprehensive picture of our software function deployment on the different controller. So we've got ESP. ESP will provide the front left, right, rear left, rear right speed, the torque reduction, the torque increase to go against wheel slip, wheel lock. We will get the torque demand from the driver inside the VCU, and we will monitor all the state also coming from usually the IBCU that got the IMU sensor, so lateral, longitudinal acceleration, yaw angle. And we will define inside the VCU individual torque target for the inverter. So the inverter, in this case, are fairly light in terms of torque path function. We have wheel slip control that respond to a maximum and minimum wheel speed calculated by the VCU. We've got anti-jerk, which is kind of a feature that already existed. But most of the supervisory control are located in the VCU. We still this loop of 80 milliseconds of latency. So that was the first implementation of DDS at Changan from our HQ colleague. So the goal of the system is to focus on high dynamic and fast response of the drivetrain. Currently, it's developed with the aim to reduce the ESP, DSC intervention, allowing enhanced and smoother chassis control than the base brake system response, and obviously a faster response of the torque at the wheel. The Changan legacy software architecture for an EV does not fully allow to fulfill these goals due to our latency of system response. So at CA UK, provided that we are now in charge of developing the software method and the integration of the next Changan inverter software, as Etienne presented earlier, we have identified some way to improve the situation and propose new deployment of the function and the strategy to be moved into the inverter. Okay, so let's look at that. In terms of quantification of why it will be more interesting to walk into the inverter rather than the VCU, I can talk about experience. When I was working at Great Wall, we had the BMW Mini project, and we had drive shaft popping up on the washboard test. Actually, at full load, every time you go onto a washboard there, due to the high torque of the e-machine, you got a really high acceleration after each washboard, and then at certain speed, you had a frequency that will come into place, and the drive shaft will pop up from the differential. So we had to introduce some torque surge damping function. We tried to do it in the VCU, but this did not work. So then we had to put, at the time, some requirement on our inverter supplier to introduce this function at the inverter level. Provided they got lower latencies, they managed to resolve this issue. Yeah. So this kind of hint that it's better to go into the inverter for this type of functionality. We want fast powertrain ESP torque intervention response also. If we look at the conventional setup with the current software architecture, the ESP is sending the torque increase or reduction request to the VCU, and then we arbitrate the torque demand, go back out on the PEU, and we get torque reduction, torque increase to go against wheel slip or wheel lock. This takes around 62 milliseconds. However, if we just bypass the PDCU, we go directly from ESP to the PEU, we can just reduce this response to 22 milliseconds, which will provide a better alignment with the ESP intervention. We also want to work on vehicle dynamics event handling before ESP correct the vehicle trajectory. Okay, I've got a slide there to talk about wheel slip control. Actually, most of the data are marketing data from BYD, from their high-tech system. They prone that it's better to rely on, in this type of powertrain, on the e-machine resolver speed rather than the wheel speed sensor. We can get an accuracy 300 times higher than the wheel speed sensor accuracy. Okay, and provided we also short loop the communication between the brake system and the inverter, we can detect the wheel slip as early as 50 milliseconds faster than the ESP can detect within the current implementation, or can counteract the current skidding event. Yeah. Okay. So this was one motive to push the wheel slip control inside the inverter. If we look now at our new proposed software architecture at Changan, so currently we still keep the driver demand in the VCU. The VCU does have other functionality. It does have some functionality related to power up, power down of the vehicle, and all the management of the interaction with the BMS. We may move that later on inside the inverter, but in this case we keep the driver demand. So we got wheel torque demand coming onto an inverter. So let's say that the rear inverter will be our lead inverter, where we got all the observer and the vehicle supervisory dynamic control function to define the individual motor torque request. We will get torque from the lead inverter, torque target from the lead inverter sent to the front inverter through FDCAN using 1 millisecond latency, not latency but frame sample rate. And for each wheel, we will have the function for lash crossing, wheel slip control, torque intervention, anti-jerk. And this can just reduce the feedback loop from 80 milliseconds to 2 milliseconds. Obviously, we need time to detect issues with the powertrain, but it will still shorten our reaction time. Yeah. So if we look at what we've done so far in terms of software development, we have worked on a wheel slip control. So if I go on the first one, yes, so our wheel slip control, by detecting faster that the wheel is slipping, can just reduce the torque to the maximum torque available on the surface, and then we get a better launch. Yeah. If we want to look at wheel slip control for slip new, we also have a faster response. So in this case, the car that goes off the track doesn't have any ESP intervention. However, we can see that without any ESP intervention, in our case, we can keep the car in straight line. We still have to have some steering wheel correction, but it's reasonable. We worked on pull drift compensation, and this comes from the observation that obviously without steering the steering wheel, but just changing the yaw target, that will have a knockdown effect on the distribution of the torque left to right, right to left. You can also steer the car. Yeah? So you can have this type of function. This is used currently in one of the BYD vehicle, the big SUV, which does steering redundancy by using obviously this concept of control of the steering through motor torque request. Yeah. And provided we can do this, if we look at the lateral acceleration and the yaw angle of the vehicle on a straight line, if there is no input from the driver, so hopefully it means the driver wants to go straight, we can also counteract any change of camber that will just push the car if the driver wasn't attentive into a ditch. And the same will apply with lateral wind. Yeah, we can just control the vehicle in a straight line. Obviously, when the driver will take over the control of the steering wheel, we would blend out the function and hand over to the different function from the EDS control strategy, which are vehicle agile steering in this case. In this case, we can show that this is a low mu surface, fairly, so sorry, it's IPG, okay, it's not Simulia, that's what we use currently. But we control the torque for each motor individually based on the different conditions. So we monitor the yaw, we monitor the lateral acceleration, longitudinal acceleration, and also the status, if we are oversteering, understeering. Obviously, if we start to oversteer, we don't want to carry on controlling the car with too much delta of torque between the left and the right, for example. We want to reduce it to allow the driver to counter steer and take over the control through the acceleration. But it's quite an effective way. So if we look at two different use cases, one without our controller active and one with our controller active, we get on this low mu surface a better tracking of our trajectory. So it does enable a safer response from the powertrain. Obviously, if you use that to go faster, you will crash at a faster speed. But, okay. What do we do in CA UK to validate this functionality? Currently, as you saw, we are using IPG CarMaker in co-simulation with our control software in MATLAB Simulink. So we got our different module. We also simulate CAN latency between the different ECU. And then we communicate with CarMaker where the track is defined and the powertrain is defined. We define our driver model, and then we run the test with or without our control strategy enabled. This is all good, but this doesn't really give us a feedback or how we performing in terms of vehicle dynamics and what will be the driver feel. So we went a step further on implementing a fairly simple driver in the loop test rig. We took a car from one of our car seat from one of our vehicle, Fanatec steering wheel with pedal on a steering wheel rack with a large curved screen, and then we can drive the car in different conditions with the driver in the loop, so we can assess the performance of our calibration. So that's the current status. We also have AVL 5-axis powertrain test bench. We don't need 5-axis, we need 4-axis with 2 DEDS. We are currently waiting to receive the DEDS unit from China, and we will mount this unit on this test bench, and we can do some dynamic tests and check the performance of the powertrain. We also have vehicle running in Chongqing, not in the UK currently. We are running 2 modified vehicles, so the Deepal G408 and the Changan CD708, which is like a Cybertruck type of car. So these cars, they've got one, I think, got 2 DEDS, one got 1 DEDS plus 1 single EDU. We will receive next year in the UK some prototype vehicle, so then we can move from obviously simulation, test on the test bench to the real vehicle and validate our concept on the track. So in terms of conclusion, currently Changan is committed to provide a vehicle with exceptional level of drivability and safety. Yeah, that's always good. At CA UK, we identified the request of architecture changes for our next generation of powertrain to improve the response time of our controller and the torque delivery and accuracy at the wheel. Our future work, we want to work toward demonstrating our DDS technology on our prototype vehicle. So this will be a bit more credible than just simulation. And we will continue to develop advanced control strategy for further enhanced powertrain performance. We also have currently merged with the chassis control team, and we will develop the next power steering, electric power steering control strategy. And this will come also with later some interaction with the active all-wheel steering system and the active suspension system, the braking system. We are going to work on this project, so it will also allow us to get more cross interaction between the different domains and improve the vehicle drivability further. Okay, thank you. I don't have a slide with question, but that's your time to ask questions.
And thank you very much. I also like this Mercedes G tank turn. This will help the
Yes.
parking problems in Munich downtown.
Yeah, I'm sure the city will send you a bill to damage the pavement.
Good. Up to you. Questions from your side.
Everybody's eager for lunch.
Thank you for the presentation. Maybe my question is a bit out of the scope of your
Sure.
presentation, but maybe you are aware of it. Just looking at this double unit, no? Double motor unit, no? Central unit, I suppose with two inverters, etc. Is Changan thought, no, when decided for this double drive unit of in-wheel technologies and how they consider, I don't know if you are aware of this.
The reality is in China, for Chinese OEM, it's really cheap to buy high power PSM motor. So overall, it's still, I believe, it's still cheaper to go on. And they like to save, you know, also. They like to be safe in their approach. So wheel hub motor may come later, but they like to go from, you know, well-known technology and make a small step and go to something a bit more advanced and move, you know, slowly. So if we understand the compliance in the drive shaft and the motor, and we got function to support that, we will move maybe toward wheel-up motor at some point. But yeah, it's provided we are looking at also some high-power vehicle. We had like a vehicle with 1,000 horsepower on 800 volt. This is high performance. So as we saw maybe earlier, the high performance for the DDS application using wheel hub may not be the best at this time. Yeah. Okay.
Yeah, thank you very much for this interesting presentation. You showed that the resolver of the electric motor is a lot more accurate than the wheel speed sensor.
Yeah.
Do you think it's possible to skip the wheel speed sensor in the future? And yeah, maybe also second question, are you considering a kind of centralized EE architecture for all these new driving functions to control vertical, lateral and longitudinal dynamics?
Okay, so we do have several platforms that will come out of the different range of vehicle. We are looking at zonal architecture, obviously to try to reduce the amount of ECU on the system. Removing the wheel speed sensor, provided that we currently still rely on supplier for the ESP, could be an issue because we don't want. I mean, you can ask Bosch to reduce, not to remove that and do some other function, but it's maybe really expensive in terms of development cost. Yes. I think currently we still need to rely on the friction brakes. So there is no intent to remove the brake system as it is known. It's currently, you know, we still see the brake system as the main safe gate for safeguarding for our vehicle. We don't pretend that we got all the knowledge, being so young in the domain. We still need the braking system to help us with maybe more extreme situation. So this is not currently the aim to remove the wheel speed sensor. That's answer your question.
Yeah. again from me, thank you for your presentation. So when your vehicles are now or will be the prototypes and also short before serial production, there is my question, how do you manage all the testing of the software until you have figured out that you will have a very, very safe system with no malfunction on the road?
That's a fair question. I'll show you first the implementation of our headquarter, which relies on high latency, so the potential for really high response, down to the powertrain is lowered, so that, the braking system may still have the advantage to curb our dynamic, provided by our torque vectoring functions. That's the safe stage before we try to implement our function. We obviously are heavily invested in simulation, and maybe so simulation we get in the currency data from the vehicle to try to replicate all the compliance and kinematic from the vehicle, and we are trying to get our virtual model as close as the real model, and then from there we will do injection of fault on the test bench to see what's happening with the system, and we will go on the test track. I believe that to get our solution to a commercial solution, we need still maybe a couple of years to do all the testing properly and validation. And we do need to develop some fail-safe function. When we detect something is going wrong, we need to bring it back safely and continuously into a safe operation of the powertrain. Yes.
A second question, please.
Sure.
Do you have a definition? How can you measure and define that you have fixed all or a special percentage of misfunction in the end vehicle on the street before you give release for serial production?
Yeah, I mean, it's kind of the same situation as ADAS system. How can you prove that a self-driving system is fully compliant? So you need to identify all your boundary use case. What's happened if you have loss of traction? You need strong monitoring. So obviously having multiple sensor as for example, the wheel speed sensor, if we don't delete it, is still there as a redundancy if we lose the resolver in the inverter. So we have to have strong, algorithm that allow us to detect that there is a failure somewhere in the system and be able to replace the signal by back calculation. We can use some Kalman filter, or we can use other sensor on the vehicle. And then in this case, we need to go into limp mode, reduce the torque output of the vehicle and the capability to split the torque. So on feedback to the driver, obviously there is a problem. But it's obviously more sensitive than just having an engine going through a transmission, and when you got problems, then maybe just open the clutch or something. It's one step further. So maybe it's why also we don't see that many of these cars out there, but we see Mercedes that try to go into this field with the G class. Yeah, I think we will move forward a better solution over time. This is by no means on the road next year, so be reassured.
Maybe it's the last question.
Okay.
Sorry. In terms of getting to production, how do you see that happening? So I think lots of people are doing all these cool things on test tracks and in prototype vehicles, but then you kind of have to go to Mr. Bosch and say, please, can you do this? Or are you thinking you'll actually do your own hardware?
So if you look at the market currently in China, I mean, I was with Great Wall Motors back until 2022. 2022. We already started a project on distributed e-drive from 2021. If you look at the Chinese OEM, they've got the Yangwang U8 on the market with 4 e-machines already. You've got the Zeekr FR01 something with 4 e-machine also. So there is already a vehicle on the market with this type of technology. And this will be a good learning curve for us. We kind of safe going later, being a follower in this domain.
I wasn't so much thinking of powertrain architecture. I was thinking about the EE architecture. So how are you going to deploy these software functions? Are you going to put libraries onto like the Bosch control unit, or are you going to make your own control unit?
The first presentation by Etienne highlighted that Changan UK is responsible for the inverter software development. So we are responsible for method and integration. So we are currently putting some of these features inside the inverter, and we will start to work them in parallel to the current mainstream features, and we will see how they react. So we will have a feature that is kind of not connected to the wheel in terms of torque delivery, but we will see how the feature works, and then we can switch it over for specific test and test track, and we will go slowly this way. Yeah. So we've got the control as the Chinese OEM move forward in terms of e-architecture. They tend to want to do everything on their own in terms of software development and deployment of the function in the different ECUs. So.
Thank you.
Thank you for the presentation.